In this video, I'm going to explain the standard reduction potential and how to use it. In my previous video, I explained galvanic cell and how they create a current, which is the result of potential difference between two half cells. If we look at this galvanic cell, you see we have right now electrode Zn and one of the electrodes is copper. And then because Zn can lose electron to copper to Cu2 plus. So we have a voltage here. We can see a voltage here that we discussed that in my previous video. But how can I measure the potential for each half cell? Something that here I measure is the potential difference between two half cells that I have here. But right now I want to find a way to find the potential for every single half cell. We cannot measure the potential for one isolated half cell, as we need both oxidation and reduction reactions to measure the potential difference. But how I can solve this problem, how I can find the potential for one half cell? To do that, we need to make cells that one of its half cell is a standard half cell. Okay, and so allocate a potential to that standard half cell that we name this potential as E. And if we know the potential of one of the half cells, and then we can measure the potential difference here. So if I know the potential of this half cell, and I can measure the potential difference between two half cells, definitely I can calculate the potential of the other half cell. So something that we need to do, we need to define a standard half cell and allocate a potential to that standard half cell. And then make a cell between that standard half cell and other half cell like Zn half cell or Cu half cell. We know the potential of the standard half cell. We can measure the potential difference, and by some calculation, we can find the potential of the other half cell. A hydrogen half cell under a standard condition is considered as a standard half cell. And an E of 0 is allocated to it. But what's a standard condition? The standard condition is temperature of 25 degrees Celsius, pressure of 1 atmosphere, and for the solution that we have here, the electrolyte or the concentration of solution should be 1 mole per liter. So a standard half cell is 1 electrode of hydrogen under a standard condition. Right now we know what's a standard condition. But how we can make a hydrogen half cell? We know to have an electrode, we need a conductor, but hydrogen is a gas, and so it's an insulator. In addition, how I can make an electrode of a gas? So let's see how we can do it. If I say I have one container like a beaker, and because I want standard condition and is electrode of hydrogen, electrode of hydrogen. So definitely my solution should be a solution of H+. And because it's a standard condition, it should be 1 mole per liter. So I need a solution of H+ here, that is concentration is 1 mole per liter. But right now I need electrode, and my electrode should be hydrogen. So something that I do, I use a tube, let's say a tube like this, and hydrogen gas, H2, and because the standard condition under pressure of 1 atmosphere, enter from here. So I have hydrogen gas entering here, but hydrogen is an insulator and also is a gas. So I need a metal, a conductor here. But I need to use a metal here as a surface that exchange of electron can happen there. But on the other hand, this metal should be unreactive, so it doesn't participate in the reaction. We know platinum is an unreactive metal, so I make electrode using that. So I do, so I have this, and then I have this, that is platinum. So what's happening here? Hydrogen gas entering from here, bubbling here, and we have H plus in our solution. So exchange of electron between H2 and H plus, that is like this. So we have H plus, 2H plus, aqueous plus 2 electron, giving us, and it's because it's just one half cell, so it's reversible reaction. We have equilibrium here, H2 gas. This exchange of electron between H2 and H plus is happening at the surface of platinum, which is a conductor. So for finding potential of different cells, so something that I do, I need to make cells that one of the half cell is hydrogen and other one is something that I want to find its potential. For example, let's say I have again 2 beakers. One of these is hydrogen electrodes, so I quickly write it H plus and the concentration is 1 mole per liter, and I have these tubes, hydrogen entering from here, and then I have this platinum, that actually exchange of electron happening here. On the other side, let's say I have zinc. Zinc in a solution of zinc ZnSO4, for example, ZnSO4, and because I want a standard condition, so again, the concentration is 1 mole per liter, and also pressure of gas here, 1 atmosphere. And definitely we need a salt bridge here, okay? And then just I use a wire to connect this two. And definitely I need a voltmeter. So voltmeter, just as soon as I connect this one, I see the needle just goes this way. What does it mean? It means Zn giving electron to H plus. The E, the potential for this standard electrode, and we say E for potential, and this dot for standard is equal 0 for hydrogen. Right now, if I read this number like 1.1, negative 1.1, so something that's it. I have this one, I know this one is 0. So this one should be, when the difference is this and this one is 0 for Zn, this one should be minus 1. So potential for Zn is minus 1.1, but still it doesn't make sense. Why for Zn? The potential that we are talking here about is reduction potential. It means these numbers for hydrogen, when I give it 0, is for reaction of 2H plus 2 electron giving H2. So then E naught is 0. So for because of that, we say reduction potential, because it's for reduction reaction. And then for Zn, so I can write for reduction, Zn2 plus aqueous gives plus 2 electron, giving me Zn S. And E naught for that become equal minus 1.1. By looking at this number, I know, okay, between Zn2 plus and H plus, definitely if they want to gain electron, if they compete for gaining electron, H plus is the winner. Why? Because its E standard is larger than E standard for Zn2 plus. But on the other hand, if I'm talking about losing electrons, so it means I have Zn and H2 competing for losing electron, definitely Zn is the winner. So Zn2 plus, between Zn2 plus and H plus for gaining electron, definitely H plus can gain electron, but for losing electron, Zn can lose electron to that compared with H2. And so because Zn losing electron definitely is anode, because oxidation happening here, and H plus gaining electron here, so it's cathode because reduction happening here. Okay, so let's go through this standard potential table that I got from the NESA website. The all reaction here, they are all reduction half equation. Because of that, we name it a standard reduction potential. And as you can see, hydrogen is 0, and all reaction on top of that, you see all of them are negative. So and at the bottom, all of them are positive. What does it mean? So if you look at here, it means all this half equation on top of hydrogen, it means because this E is for gaining electron, it means all of them have less tendency for gaining electron compared with H plus. So if there is a competition between H plus and any of these ions for gaining electron, definitely H plus is the winner and it gains electron. But if you look at these elements, you see all of them, they have E, positive E. So it means if there's a competition for gaining electron between H plus and let's say Ag plus, definitely Ag plus can gain electron. But let's look at this. So right now I have Mg here and Zn here. So when I'm talking about these two, which one can lose electron to other one? Definitely because Mg is on the top, so it can lose electron to Zn, but definitely if I have Zn2 plus and Mg2 plus that both want to gain electron, definitely between these two, Zn2 plus gains electron. So something that is on top is better for losing electron, and something at the bottom is better for gaining electron. Right now, let's look at these two. For example, I want to see if I can have a reaction between MgS and Zn2 plus, if it's possible to have this reaction. I look at this, I say, okay, Mg and Zn2 plus. If I want to have reaction between these two, I know in this reaction, it means Mg should give electron to Zn2 plus. Is it possible? We look at this, Mg is on top of the Zn, so it means it can lose electron to Zn2 plus. So this reaction can happen. Right now, I want to see if the reaction between Sn2 plus and Pb can happen. Pb S plus Sn2 plus aqueous. I see Sn is on the top. If we should see if Pb can give electron to Sn2 plus. No, it can't, because Pb is something that likes to gain electrons. If there's a competition between Pb and Sn for gaining electron, Pb is the winner. So definitely Pb is not going to give electron to Sn. So no reaction is happening.